Over 3,000 miles below the surface, right at the centre of the Earth, lies a solid spheroid. Primarily made of iron, and nearly as big as the Moon. Its temperature rivals that of the Sun. This is Earth's inner core. It spins independently at the very heart of our planet. And while we can't see it for ourselves, its immense heat triggers processes that impact us all. Plate tectonics that manifest in some of the most awe-inspiring and deadly sights on the surface. Our planet's invisible magnetic field, which makes life possible. It's no wonder that Earth's core has captured the imaginations of generations of scientists, who have developed ever more sophisticated instruments to investigate its fiery depths. And the latest research efforts have yielded discoveries that could have come straight from a Hollywood film. Our inner core appears to not only have stopped spinning, but has in fact started moving backwards. Why has this happened, and what does it mean for us topside? I'm James Stewart and you're watching Astrum Earth. Join me as we quite literally explore our planet's deepest, darkest secrets. We'll investigate its inner workings, assess the implications of our core's change in motion, and ask the question, how worried should we be? In order to get to our planet's core, we need to go down. Call it my version of a journey to the centre of the Earth. Each layer has its own role in creating, sustaining, and sometimes destroying the world above. And all of them are influenced by the solid iron heart. Here at the surface, we walk upon the crust, a mere brittle shell. Though it feels pretty solid to us, it is in fact fractured into giant tectonic plates that drift, collide, and grind past each other, causing violent earthquakes and devastating volcanic eruptions. How it moves is all thanks to the layer below, the mantle. This layer also appears solid, but is actually flowing very, very slowly, at the rate of a few centimetres a year. This tiny but inexorable movement contributes to the plate tectonics that impact our surface world. Dig deeper still and you reach the outer core, a sea of iron and nickel with its own heat-driven currents. Its motion generates the Earth's magnetic field, which protects life on our planet from deadly solar particles. Finally, suspended in this outer core is that primarily iron inner core. Here, the temperature reaches 6,000 degrees Celsius. Due to the immense pressures, the metal isn't liquid but solid, forming a spheroid shape, like a slightly squashed sphere. This is our planet's boiler room. Its heat triggers the processes in the layers above, driving those all-important convection currents in the outer core and, ultimately, contributing to the plate tectonics that shift the Earth's crust. It's easy to take for granted that we understand our planet's structure, but in reality that knowledge was incredibly hard-won. It's one thing studying, cataloguing and theorising about the world we can see all around us, but quite another to investigate our planet's hidden interior. So how do we know what's down there? In Frankfurt, September 1896, darkness was falling as a 34-year-old Emil Wiechert waited for his chance to speak at a meeting of German scientists and physicists. Clutched in his hands was his latest research, which proposed a solution to a problem that had plagued the scientific community for more than a century. You see, the average density of planet Earth had been calculated at around 5.5 grams per centimetre cubed, and yet surface rocks have a density of around half that. So where was that missing mass? One theory was that the Earth gets progressively denser nearer the centre, but that wasn't good enough for Wiechert, who reasoned that molecules in a solid are already pretty densely packed, and even the compressional effects of high pressure wouldn't be enough to achieve the density required. And so, when he finally got the chance to speak, he proposed something else. His theory was that the density difference must be due to there being a different, much denser material hidden deep in Earth's interior. As to what that material could be, well, the inspiration for his theories came from the heavens, in the form of iron meteorites. These little clumps of metal have a density higher than the average of Earth, and Wiechert reasoned that our planet's interior must therefore contain a large iron core, dense enough to account for the difference between lighter surface rocks and the higher planetary average. Now, this wasn't an entirely new idea, but not only had Wiechert deployed mathematical reasoning rather than the purely theoretical work of his forebears, he'd also proposed it at just the right time. A new technology was emerging that would finally allow the interior of the Earth to be studied. Earth's core is so deep and the pressures and temperatures so intense that you can't simply drill down there and take a sample, although that would be nice. Even today, our deepest man-made hole is the Kola super deep borehole in Russia, and at more than 12 kilometers deep, that is still only a fraction of a percent, 0.2 to be exact, of the way there. And so, in order to study the core, scientists rely on measurements taken here on the surface. Now, thankfully, there's one way we can get particularly insightful information, and that is from earthquakes. By the 19th century, increased interest in seismic activity had prompted the creation of a device to measure them scientifically. Yeah, this was the modern seismograph, and it looks something like this. For the first time, the analysis of seismic events weren't based on eyewitness observation and hearsay, but on quantifiable data, which we love here on the channel. But while the device itself was unquestionably a scientific breakthrough, the real magic happened when the invention spread across the globe. As seismographic networks expanded, scientists found they could detect earthquakes happening as far away as the other side of the planet. In 1897, the so-called Great Earthquake erupted at Shillong Plateau in India. Shocks were felt in Calcutta and even as far away as Burma. But seismographs detected this earthquake much, much further away, in Europe, where the seismograms they created were pored over by British geologist Richard Dixon Oldham. Leader of the Geological Survey of India, Oldham noticed that the seismogram showed 3 distinct wave shapes. In his papers, he compared the data found from this and several other earthquakes, and found that they too showed the same 3 waves. The reason he could see them was, being far from the epicenter, differing speeds of the waves meant they arrived one at a time. The first arrivals were later known as primary waves, pressure waves, or P waves, which are longitudinal. They oscillate in the same direction as they're travelling in. These were then followed by secondary, shear, or S waves, which are transverse. Their oscillations are perpendicular to their direction of travel. Finally, surface waves ripple through the Earth's crust, and it is these that tend to cause the most destruction. It had already been established by this point that longitudinal waves can pass through both solids and liquids, but transverse waves can only pass through solids, and you can probably see where this is going. Since the seismic waves had travelled through the inside of Earth to reach the seismograms, the resulting seismographs could yield information about what they passed through, namely, the structure of Earth itself. This realization would allow centuries of speculation to finally be put to rest. Put simply, Oldham noticed that waves that had travelled a long way to distant seismographs seemed to travel much slower than the 6 kilometers per second it usually moved through the mantle. To explain this, he concluded that they had traversed a central core, composed of matter which transmits them at a slower speed, 3 kilometers per second to be exact. He calculated the size of this core to be 4/10 of the Earth's radius. deduced that it bends earthquake waves, and that it behaves fundamentally differently to the rest of the Earth's interior. But he did not speculate as to what this core might be made of, refusing to go beyond what he could prove with data. And so by the early 20th century, you had a theory that the Earth had an iron core, and apparent proof that some sort of core did in fact exist. We were finally beginning to crack the inner structure of our planet, and yet despite these great strides, these pioneers missed something. Sometimes I get so focused on all the awesome stuff happening below our feet, I forget that the stuff on land also needs a bit of love too, perhaps now more than ever. That's where our friends at Planet Wild come in. They are a community-based nature protection organisation fighting back. Think of them like crowdfunding but for nature. Each month, their community funds a project to restore nature around the world, and then documents it with a YouTube video report, so you can see the impact of your contribution. It's actually their transparency that inspired us to become members in the first place. And with so much plastic waste around, especially at this time of year after Christmas, one of my favourite projects they're working on right now is a breakthrough that could stop plastic from reaching the oceans. Now, my background is actually in sustainability, and I'm very, very personally invested in what these guys are doing. So much so, I wanted to give as many of you the chance to get involved too. The first 100 people to sign up to Planet Wild using my code Astrum1 will get their first month paid for by me. Yes, just scan the QR code on screen right now or click the link in the video description. And the best part, you'll immediately have an impact and see the results in less than 30 days, as we head back to the video. As seismographs continued to spread around the world and more data was gathered for scientists to pore over, they noticed that S waves didn't register on some seismographs. Something was stopping them. Now, remember I said that S waves don't transmit through liquids? Well, it was a small leap, therefore, to go from that fact to the idea that Earth's core must therefore be liquid iron. It wasn't completely wrong, but there was something they had all missed, and it took a Danish scientist to find it. In 1929, Inger Lehmann was chief of the seismological department at Denmark's State Geodetic University. Her responsibilities involved keeping the instruments correctly adjusted, interpreting the seismograms, and publishing the bulletins of these seismic stations. But her job did not extend to original research. So, when she decided to embark on her own research project, she had to do so alone, without the typical team of assistants to help her. But it was precisely because she was forced to trawl through so much data by herself that she noticed something odd about the P waves she was studying. You see, if the Earth had a liquid core, P waves should travel down from an earthquake, reach that core, and be refracted due to the liquid's properties, like light entering a prism. The expected result would be a shadow zone, where no P waves would appear, because they had all in fact been refracted away. Yet after an earthquake in New Zealand, she discovered P waves in the shadow zone, precisely where they shouldn't be. In a paper titled simply P, she attempted to explain what she had seen and reconcile it with existing observations, concluding that the core had two parts. An outer core that was liquid and so stopped the S waves, but crucially, also an inner core that was solid, so could transmit some P waves to the shadow zone where she'd seen them. As a woman working in the male-dominated world of science, Inger had to fight to have her conclusions heard, but she would turn out to be absolutely correct. That solid inner core was the final piece of the puzzle. However, as is often the way with scientific research, this discovery simply paved the way for more questions. Since the solid inner core is held within a liquid outer core, does it necessarily spin in sync with the rest of the planet, or could it be rotating at its own speed? To find out, scientists would require incredibly sophisticated seismographs, and they would soon have access to such instruments. Although it would not be thanks to pure science alone, but to war. Well, kind of. By the second half of the 20th century, the world was in the midst of the Cold War. But while the general public lived with the spectre of nuclear Armageddon, for seismologists, it was proving to be a time of incredible excitement, as the United States instigated Project Velar Uniform. Its aim was to develop a suitable system for detecting underground nuclear testing in the Soviet Union. And what resulted was an investment of over $500 million in today's money in seismographic technology and networks. Crucial to the project's success was the ability to distinguish between the seismic waves produced by nuclear tests and those made by naturally occurring earthquakes. And so by the time the Cold War ended, researchers at Harvard University had made breakthroughs using these seismographs. They showed that seismic waves travelling along Earth's north-south axis through the inner core moved faster than those undertaking the journey in an east-west direction. To explain this speed difference, they theorised that the Earth's core is anisotropic, meaning it has a crystalline structure aligned with Earth's rotation roughly along its magnetic field. Think of it like the grain on a plank of wood, and just as a plank of wood is easier to mill in one direction than the other, it's easier for earthquake waves to pass through the core on the north-south axis than the east-west. Well, almost. It turns out that this crystalline structure doesn't align precisely with the rotation of the Earth, but rather is tilted a few degrees off-axis. This was crucial, because it gave scientists a potential way of determining how fast the inner core spins. If it spins at a different rate to the rest of the planet, then that would continually change the way those crystals are aligned with the rest of the Earth, which would in turn affect the wave travel. This realization gave birth to a method of assessing inner core spin that is still used to this day. Now, working out whether Earth's core was spinning at its own rate wasn't easy. Scientists recognized they needed data from multiple earthquakes that had happened in nearly the same spot, but far enough apart in time that the core could have moved. Fortunately, they had decades of earthquake data thanks to the Cold War, and so the hunt was on for what they termed earthquake doublets. Now, such doublets are incredibly rare. Imagine hunting for identical twins when they're sat in different parts of a crowd at Wembley Stadium. Fortunately, it was no longer the era of pen and paper, and with the increased digitization of seismic data, what would have once been thousands of human hours was now the work of algorithms. By 1996, a team of researchers at Columbia University had found what they were looking for: data from a series of earthquakes that took place in close proximity, at the South Sandwich Islands, and also, crucially, a seismic station that had reliably monitored them for 32 years at College, Alaska. By comparing the readings, they found that from 1967 to 1995, these similar waves were taking a faster and faster path through the Earth's core. They had their answer. Earth's core must have rotated at a different speed to the rest of the planet. It was the first observational evidence of inner core rotation, and they calculated that it was spinning faster than its surroundings. And now, with the technique proven, well, the floodgates opened. In the last couple of decades, some studies have been published that agree the core rotates faster, while others have concluded that it spins more slowly. Further studies have suggested that it fluctuates, sometimes spinning faster and other times slower, maybe as frequently as every couple of years. So what's actually going on? Who's right? In 2023, scientists at Peking University in Beijing published a new research paper, arguing that inner core rotation has nearly paused and, relative to the mantle, has actually been rotating slightly backwards over the past decade. They stated that such a change of rotation also occurred in the early 70s, ultimately concluding that the Earth's inner core oscillates with a period of about 70 years. The following year, another study was produced, this time by the University of Southern California, which approached the same problem from a subtly different angle. Rather than looking for differences in waves from the same earthquakes, it looked for matching waveforms from different times, reasoning that if previous studies were correct and the inner core did go through a cycle of faster and slower rotation, then there would be times where, relative to the mantle, the inner core was back in the same position. I think of this like a car and a bus driving in the same direction side by side. If the car alternates between travelling slower and faster than the bus, then there'll be times when it's ahead of the bus, there'll be times when it's behind, and times when it's back aligned with the bus again. So the study examined P waves produced from 121 earthquakes that took place between 1991 and 2023 in the South Sandwich Islands. The waves passed through the Earth's inner core and were detected by seismometers in Alaska and Canada. Using this methodology, they confirmed the findings of the previous year, that the changes in the inner core's rotation speed follow a 70-year cycle and, more than that, according to their calculations, it's just about due to speed up again. As for what causes this change, well, scientists aren't yet certain. Possibly the magnetic field of the liquid outer core could drag on the solid iron within, speeding it up or slowing it down, while gravity from dense regions in the mantle could pull on variations in the inner core affecting its rotation. But what does that mean for us? Do we need to worry about this? Well, remember how I said earlier that the inner core is like the boiler room of our planet? Well, it turns out that changes in its behaviour do seem to correlate with other phenomena on the surface. The authors of the 2023 study noticed that 70-year oscillation coincides with fluctuations in the length of a day and changes in the magnetic field. And beyond that, they even linked them to changes in global mean temperature and sea level. But before you're too alarmed, we're talking about tiny changes here. 1,000th of a second here, a fraction of a degree there. Certainly not enough to explain global warming. The long story short is it's early days. Scientists are continuing to study the inner core and its impacts on the world above. And with every passing year yielding more and more seismic data ripe for analysis, new insights are only a matter of time. Perhaps Inga Lehman put it best. A few years before her death, at the ripe old age of 104, she wrote, "The first results for the properties of the inner core were naturally approximate. Much has been written about it, but the last word has probably not yet been said." Let me know in the comments what you think of this. Is this something to worry about? How do you think this will affect life on Earth, if at all? It appears that when it comes to the deepest, darkest secrets our planet holds, we really are still only scraping the surface.